So question 21.42, it says using cyclopentanone as your starting material and using any other reagents of your choice, propose an efficient synthesis for each of the following compounds. Well, you notice the first one has a 1, 2, 3, 4, 5, right? There's a 1, 5 functionality, right? We have a carbonyl at carbon 1 in this numbering system, and we have a carbonyl at carbon number 5. So with that, we're going to think about Michael addition. And so if we're going to start with cyclopentanone, then here's the alpha carbon. We would break this bond right here. And in terms of our retrosynthesis, we'd start with cyclopentanone, but then we would have a Michael acceptor, which would look like this. Okay, that would be our Michael acceptor. But we know that cyclopentanone is not a good Michael donor, right? Because if you make the enolate of cyclopentanone, you're going to get a mixture of 1,2 addition and 1,4 addition, which isn't very helpful. But luckily, we know that there is a way around that, right? If we just take the cyclopentanone and we convert it to an enamine, then it's going to do the storic enamine synthesis, and we're going to have a good Michael donor. So the first step is that we're going to treat this with a dialkyl amine, a catalytic amount of acid, and we're going to lose water. Okay, that's going to give us our enamine. All right, the enamine will look like this. I'll just draw it right here. I'm going to delete it after, but this is what our enamine will look like. Okay, and then the enamine is a good Michael donor to our Michael acceptor. Okay, so there's our Michael acceptor. So in the second step, after we formed the enamine, we're going to add the Michael acceptor, which would be this alpha beta unsaturated ketone, like that. That's going to give us the iminium ion and the enolate. And then in the last step, we just treat that with aqueous acid and we heat it up. So our intermediate, I'm not going to draw the intermediate. I'm just going to put here step number 3 is aqueous acid. And there we go. That's going to give you the final product like that. So there you go. That's a storic enamine synthesis. So we'll write that down here. So we'll put storic enamine synthesis. All right, the next one, you can see that you've got 1, 3, right? We've got 1, 2, 3 functionality, and so we're thinking an aldol reaction here. It's not an aldol condensation. It can't be because we don't have a double bond here. So this must come from an aldol addition. So if we look at the alpha carbon of our, what would be the cyclopentanone, we break this bond here. Then in terms of our retrosynthesis, we've got the cyclopentanone, and then we would have this as being our aldehyde that we would start with. Now, of course, if we take this and we just, put this in sodium hydroxide without heat, that would do an aldol addition, but then we end up with a hydroxyl at this position, and we want to end up with the methyl ester, or the methyl ether rather. We want to add a methyl group to there. So I've got an idea. How about we take the cyclopentanone and we treat that with LDA? Right? If we were to treat this in the first step with LDA, that's going to completely deprotonate this to make the enolate. Then if we treat it with the benzaldehyde in the second step, what's going to happen is we get a nucleophilic attack like this, and that's going to produce this intermediate. So let me draw the intermediate that we're going to get. It's going to look like this. Okay, like that, and put my phenyl here. If you're wondering where the proton is, I'm just leaving this proton out. It's right here. I'm just leaving it out. So we'll put that there like that. And so then we end up with this enolate, or this alkoxide, I should say. And so all we got to do is treat that with iodomethane in the last step. So we'll treat this with methyl iodide or iodomethane, same thing either way. And we do an SN2 reaction like this, and that is going to give us the final product. So it's kind of like, doing a Williamson ether synthesis, with the intermediate that's formed. Okay, so this I would call it like a directed aldol reaction with kind of like a Williamson ether synthesis thrown in there. Let's take a look at 21.45. So this one says propose an efficient synthesis of each of the following. So we have an alpha beta unsaturated ketone here. We have substitution at the alpha position. We also have substitution at the beta position. And you remember that I showed you how to do this once we get into section 21.7. So this comes from section 21.7, where first we're going to treat the ketone, the alpha beta unsaturated ketone rather, with a Gilman reagent. So we're going to take this, and in the first step, we're going to treat it with the methyl Gilman reagent like this. Now what that's going to do, it's like having a negative charge on your methyl, and it's like doing this. Okay, so then you're going to end up with an intermediate that looks like this, where we have the negative charge here on our oxygen. So then what do we have to do? We have to treat it with an electrophilic source of a benzyl. So that means we're going to treat it with benzyl bromide or benzyl iodide. So we'll just write benzyl iodide. And then that is going to attack at the alpha carbon like this. And that is going to give us the desired product, where we have the carbonyl, we have a methyl group here, and we have the benzyl group over there. So in essence, what you're doing is in the first step, you're treating it with the methyl cuprate. And then in the second step, you're treating it with benzyl bromide, which is this compound right here. Just a quick two-step reaction sequence in order to make this compound. And then for the last one, we have an alpha beta unsaturated aldehyde. And we're trying to figure out how to make this alcohol here. Well, you can see that you've added something at the alpha carbon here, and you've also added something at the beta carbon. So we're going to use a similar strategy to what we did the last time, right? If we were to take this molecule, the starting material, and if we were to treat this with the methyl cuprate is what I should call it, you're going to end up with an intermediate that looks like this. So you've got your methyl group here, you're going to have the double bond here, and then you're going to have this enolate, okay? Then if you want to add this second methyl group, we'll treat it with methyl iodide. Then we're going to get the enolate acting as a nucleophile like this, and that's going to give us this intermediate. Actually, this is a product, not really an intermediate, is it? But you're going to end up with this, okay? There you go, the aldehyde. And if we want to make the alcohol from the aldehyde, all we have to do is reduce it. You could use lithium aluminum hydride followed by treatment with water, or you could just use sodium borohydride. That works too. So we'll put sodium borohydride in methanol. It could be ethanol, it could be water. Either way, there you go.